Welcome to the fascinating world of binary numbers, the language of computers and digital technology. In this video, we'll dive into the fundamental concept of binary, a numerical system that uses just two digits, 0 and 1. But why should you care about binary? Imagine a world where only these two numbers represent all the information, images, and videos you encounter. It's a secret code that powers the digital world. Binary can be seen on light switches, Morse code, logic gates, and many more. The numbers we use today are called base 10 or decimal numbers. Decimals are the numbers we use daily, such as counting, mathematical and statistical equations, and many more. These consist of the digits 0 through 9. Now that we know what these two number systems are, let's head into our lesson, converting one number system into another. That we have learned about decimal and binary numbers, we will be trying to convert one to the other or vice versa. But first, we have to learn about positional notation because this will help us in today's lesson. So, what is positional notation? Positional notation is when you shift the digit to the left every time you reach 10 times its value. So in decimal, we go from 0 to 9. But when we add another number, which is 10, we add a digit to the left of it. And then when we reach 10 times that value, which is 100, we add another digit, we shift it to the left again. Same for 1,000, 10,000, and so on. This is essentially the same thing for binary numbers, but since we only have the numbers 0 to 1, we can only do the 2 times its value instead of 10 times its value. So we have, let's say, start with 1 in binary, and then 2, and then 3, and 4. See how we shift the digit every time we reach 2 times its value. So how will this help us in today's lesson? Let's say we have the binary code 1 0 1 1. How will we convert this into its base 10 form or binary form? Since we know that binary shifts its digits to the left every 2 times its value, we can say 1 0 1 1. So we start here 1, then 2, then 4, then 8. See here that it increases 2 times every time we shift to the left. So now that we have this, we look at the ones only when we ignore the 0. Look at the value on top of these. So the value which has ones, now that we know about positional notation, this will greatly improve how we convert binary to decimal numbers and even binary to octal numbers. So let's say we have the binary number 1 0 1 1. So how will we convert this to base 10 or its decimal form? Now, knowing that we have the positional notation now, and that in binary it shifts left every time it reaches 2 times its value, we should rewrite this. So we start with 1 and then multiply that by 2. So we have 2, then multiply that by 2, we have 4, then 8. So you see here that there are values on top. Now, to convert this to base 10, we only get the values of the numbers on top of the ones only. So we have here 1, 2, and 8, which are the ones with the ones on it. So now that we have these values, we simply just add them. So we have 8 plus 2 is equal to 10, and then plus 1, which is equal to 11. And that's how we get its base 10 form. But make sure to add a sub 10 there to understand that this is in a base 10 form to prevent confusion. Yeah, we should probably do that for the binary too. So we should add the 2 here at the bottom. So this is to prevent confusion. Now that we know how to convert those values to decimal, let's do a bigger number. Let's try one. So we have 1, 1, 1, 1, 0. Now, let's convert this to decimal form or base 10. So, just as before, you take the value and then you add the numbers on top. See here that it doubles every time you go left more. So, now that we have the numbers on top, we simply just add the numbers that contain number 1. So we have 16 plus 8 plus 4 plus 2. So you have 16 plus 8, which is 24, and then plus 4, which is 28, and then plus 2, which is 30. So now we have 30 base 10. That's our final answer. And that's it. That's how you convert binary to base 10. It's very simple, and it shouldn't take you long to master this. So now that we have learned about conversion of binary to decimal, I want you to try these 3 examples yourself. You can pause the video to try it now, and then we'll solve it together. So we start off with number 1. Write down the given number, 1, 1, 1, and 3 zeros. Now, to convert this to decimal, it's pretty easy. Rewrite this 1, 1, 1, 0, 0, 0. Now, what we just do is, remember, we start with 1, and then double that, 2, and then we double that again, 4, 8, 16, and 32. So, what do we see here? We see 3 digits, 1, which has a value of 8, 16, and 32. So we write down 32, 16, and 8. So what happens? We just add all these numbers up, and then that's how we get the decimal number. So 32 plus 16 is 48, and then 48 plus 8 is 56. There you go. 56 would be our decimal number. Don't forget to add the 10, the bottom right, the number, to prevent confusion. So, move on to number 2. Same thing as before. You write down 1, 1, 0, 1, 1, these 2. We rewrite it and space it out so we can read it better. So here we see that numbers 1, 2, 8, and 16 are the ones that have ones. So 16 plus 8 is, 16 plus 8? 24. So what's 24 plus 2, which is 26. 26 plus 1 is 27. So our answer is 27 base 10. So for the last number, we have 0, 1, 0, 1, 0, 1, base 2. So 1, 2, 4, 8, 16, 32. So you have 16 plus 4 plus 1. So what's 16 plus 4? 20 plus 1, which is 21. So the decimal number would be 21 base 10. There we go. That's how you convert binary numbers to decimal. It's pretty easy. So we'll move on to the next lesson.
Octal numbers, or what we call base 8 numbers. Octal numbers uses the digits 0 to 7. So when we convert octal numbers into binary, we will limit it to 3 digits. For example, since octal value is only limited to 7 counts, our binary number consists of 3 digits. So for every 3 digits in our binary number, we need to cut it from here, left to right, always. We need to cut this, there. From there, you need to count the binary. So from 1 to 4, this is all you need. Because of 1, we need to put 1. Because of 0, 0, 4, for this one. Just like here. Since this is 0, automatically is considered as 0. So we will add this. 4 plus 1, 4 plus 1 equals 5. So our octal number in this binary is 55. Here's another example. First step, we need to cut it by every 3 digits. 1, 2, 3, cut. 1, 2, 3, cut. And then we will get its value. The first one is 1. Same here. So since this is only 2, we can just put some imaginary 0 here. So 1 and 2. Remember to add these two, and our value will be 3, 1, 1. This is our octal value. Here's the exercise for the octal value. You can pause the video to solve it yourself or continue to play it to show the answer. So here's the answer on the exercise on the octal. Also guys, don't forget to put your base number on the lower right side of your answer, right here. Here we have our hexadecimal. Hexadecimal uses the digits 0 to 15. It is also used to define colors on the web. It uses letters from the alphabets as a representation of the numbers 10 to 15. So just like from the octal that uses, why can't I write? Octal that uses 0 to 7, its binary number is consisted of only 3 digits at max. In hexadecimal, it goes from 0 to 15, which consists up to 4 digits. So if you put like this, our binary, to convert this into a hexadecimal, we need to split it by every 4 digits of the binary. So 1, 2, 3, 4, split 1, 2, 3, 4. From there, you will do the conversion. So as always, 1, 2, 4, and 8. Since there are all 4 digits on hexadecimal, we'll also use up to 4 digits in binary. So 0 comes to 0, second one is to 2, third is to 0, the fourth digit, or should I say, is 8. The other side. First is to 1, the second is to 2, the third is a 0, so we'll put 0, and the last is 8. From there, we will add these digits. So since the only available digit here is 8 and 2, it becomes 10. From here, 2, 1, and 8 is equivalent to 11. From the last slide, we can see that 10 is equivalent of into A and 11 is to B. So our hexadecimal is B, A, base 16. As another example of converting binary into a hexadecimal, you can just put here. Just like that. Just like what I said, every 4 digit of the binary, of course, you will go from right to left. So 1, 2, 3, and 4 will split 1, 2, 3, and 4. Split. So just like that. And we can just put some imaginary zeros here to become 4 digits. So our basic binary, 1, 2, 8 comes into 1 into 1, 0 into 0, third place of is 1, so we will put 4, last is 8. Here also 1, so 0, 0, and 8. Again 1, and then 2. We will add this. So 1 plus 4 is 5. 5 plus 80 plus 5, 8 is equal to 13. Here, 1 plus 8 is 9. 1 plus 2 is 3. So our hexadecimal is, sorry, I forgot the base number. Our hexadecimal is 3, 9, and what is the the alphabet of 13 is D. Of course, don't forget the base. So here are the exercise for hexadecimal. I like you guys to try this. Try to convert this binary into a hexadecimal value. You can pause this video if you want to do it yourself, or you want to continue playing it to show the solution. So here's the solution for the hexadecimal. Congratulations everyone. We've covered a lot in this lesson on binary conversion. From binary or base 2 to base 10 or decimal. From binary to octal and binary to hexadecimal. Understanding these understanding these conversions is a significant step in your journey to mastering the world of computer science. But guess what? This is just the beginning. I know the importance of building a strong foundation in these concepts, and the good news is we've got more lessons lined up just for you. In the next lessons, we'll delve deeper into the binary operations, explore real-world applications, and equip you with skills that'll serve you well in your academic and professional journey. So stay tuned, like, subscribe, and hit that notification bell. If you have any questions or specific topics you'd like us to cover in these upcoming lessons, drop them in the comments below. Together, we're going to become binary experts, one lesson at a time. Thank you for joining us today, and I'll see you guys the next one.